I'm happy to to introduce Alan Haynes from University of Houston. He's also the Texas, and we invited Alan several years ago to our conference, discrete geometry conference, in the island. But I'm surprised when I open. I don't know when you submitted this paper to the archive.
This one that I'm talking about today?
Yeah, when?
That was like last year.
Yeah, last year, but okay. When I open archive, one moment, when I look at this paper, I'm surprised. Just it's recently I enjoyed.
I was surprised too.
Yeah, it is actually. It is maybe not too good to say something advanced, but believe me, it's a beautiful paper. Beautiful.
Oh, thank you.
This paper. Okay,
well,
please start.
Yeah, so I'm going to talk about something which is a little bit, maybe seems unrelated, but it turns out that it's related to these optimization problems in discrete geometry, like the kissing number problem, at least, or some problems like it. And so my goal is to kind of try to explain how gaps problems from Diophantine approximation can be reformulated in terms of certain discrete geometry optimization problems. A lot of what I'm going to talk about is joint work with Jens Markov from Bristol. And maybe just to start with, to give you guys a little bit of background, because there's probably people here who don't know some of the more basic stuff, I'll just tell you, my talk is going to be really easy. I'm going to hide a lot of details and just try to explain what the underlying ideas are. But I want to start off by just telling you this classical theorem called the Three Gap Theorem or Three Distance Theorem. It's also called the Steinhaus problem. It's got a bunch of different names, and it's also got a bunch of different proofs. There's like a dozen different proofs in the literature, at least. So this is the setup. You pick a real number alpha and a natural number n, and then you consider the points little n alpha mod 1, little n going from 0 up to big N. This set I'm calling Sn. When you take that set of points off the circle, you're left with component intervals. I'll show you a picture in just a minute here. And if you let Gn denote the number of distinct lengths of component intervals, then what the Three Gap Theorem says is that that quantity is always bounded above by 3. And when you first see this, you might think that you're reading it wrong, but it's really true. It doesn't matter what alpha and n you pick. When you take these points off the circle, you're always going to have at most 3 distinct distances remaining. So here's a little picture just to make sure that everybody understands. In this example, I'm taking alpha to be the square root of 2, n equals 12. So you put these points 0, alpha, 2 alpha, and so on the circle, and you look at the gaps. You look at the lengths of the intervals between consecutive points. And if you do that in this example, you see that there's exactly 3 distances. There's a red distance and a blue distance and a purple distance. There's another feature of this theorem. I'm not going to say much more about this, but it turns out also that when there are 3 distances, the larger one is the sum of the smaller 2. So that is also sometimes part of the statement of the theorem. Okay, I'll come back to this in a little bit, but what I want to mention now is that there are many generalizations of the 3 distance theorem to higher dimensions. There are lots of different ways to generalize it, either to a higher dimensional torus or to study linear forms, or in lots of other ways. And I'm not going to talk about all of these. I don't have time for that. But the main one that I want to talk about is this one in green about extensions to higher dimensional tori. So I'll do that. But before I do that, I want to sort of set the context a little bit and just go one step before sort of historically and talk about gap problems for linear forms, because this is kind of how I got interested in this problem. And it was maybe about 10 years ago when I started to think about gap problems for linear forms. So first I'll tell you just pretty briefly about gap problems for linear forms, and then I'll talk about the generalization to the higher dimensional torus, which is where you see more of the discrete geometry type problems coming in. So one way to generalize this, and this may not seem to you as the most natural way, but one way to generalize this 3 gaps problem is to consider the collection of all linear combinations m alpha plus n beta, where alpha and beta are 2 real numbers. And the integers little m and little n now are running over a rectangle, or maybe even some other region in space. So in my definition here, the little m and little n are running over a capital M by capital N rectangle. These are points on the circle. So when you remove them from the circle, again, you're left with component intervals. And you can then ask, how many distinct lengths of component intervals do you see? So that quantity is what I'm calling G of Mn. And that has been studied by many people. It seems kind of arbitrary, but it's something that's related to certain other problems. Like, for example, there's some problems in physics where understanding what this quantity is important. And so there are a lot of people who have looked at this over the years. I mentioned a few names down at the bottom. So I'll tell you a little bit about the Erdős and Gielen and Simpson, their conjecture for GMN. There's also work by Avi Frankel and Ron Holzman, by Nicolas Chevalier, by this five-author team, Bleher, Homa, G, Roeder, and Shen. This is all really interesting stuff I could tell you about, but I'm going to have to move a little bit quicker to get through it. And also by Michael Bosher-Neeson and Freeman Dyson. So I'm going to skip some cool stuff and just tell you where I kind of got. There's this little, and it's in a paper by Gielen and Simpson. And the conjecture was that if 1 alpha and beta are linearly independent over the rationals, if you look at the values of g of n, so here they're sampling over squares, that the number of gaps that you see should be an unbounded as a function of capital N. So that was the conjecture of Erdős in the paper of Gielen and Simpson. And there's a reason for assuming that 1 alpha and beta are Q-linearly independent, because when they're Q-linearly dependent, the supremum here is finite. Okay, that conjecture turned out to not be correct. They didn't actually state it as a conjecture. They just sort of stated it as a question. Okay, but it turned out to not be. It turned out to not be correct, and that was first observed by Michael Bosher-Neeson and Freeman Dyson in a private correspondence between them. And then later on, the Bosher-Neeson and Dyson argument was formalized and written up and expanded in the 5-author paper that I mentioned before. And what they proved in that 5-author paper is that actually, if you look at the collection of pairs of points alpha beta for which the supremum is finite, that set has Hausdorff dimension 2. So that automatically tells you, that right away tells you that there are other values of alpha and beta besides alpha betas which satisfy the hypothesis of this problem for which the supremum is finite. Now, there's another reason why people are interested in this problem, is because it's very closely related to a famous problem in Diophantine approximation called the Littlewood conjecture. So in connection with the Littlewood conjecture, what you'd like to be able to prove is that for some value of alpha and beta, the supremum of GNN is infinite. If you can prove that that's true for some value of alpha and beta, then you prove the Littlewood conjecture for that value of alpha and beta. The thing is that even though the original conjecture of Erdős, Gielen, and Simpson turned out to be false, there was still the open question of whether or not there even exists a value of alpha and beta for which the supremum of GNN is infinite. And nobody could prove that there's even one pair of alpha and beta for which that's true. But then one time I invited Jens Markov to come for a colloquium talk in the University of York when I was in York in England. And he had a really good idea. And his really good idea was to try to reformulate this problem as a problem about functions on spaces of unimodular lattices. And it turned out to be a really great idea. And after we took that idea and sort of ran with it, what we're able to prove is that for almost every choice of alpha beta, so in the generic situation, the number of gaps in is actually infinite. So this is the kind of background, and this is how we first started. This is how we first started to bring the connection to the space, to functions on spaces of unimodular lattices, into these problems about higher dimensional gaps. Okay, now I'm going to tell you about the other generalization of the three-distance theorem, which is maybe more natural from a geometric point of view. So the other generalization is generalization to rotations on higher dimensional tori. So here, I'm going to show you a couple pictures again in just a minute to make sure that we understand the definition. So you look at the points, little n alpha modulo the integer lattice in gap, and so you one natural n here. I'll also mention, it's important also here that we're considering this with respect to the Euclidean metric. I'll say a few things about the Supernorm metric as well, but in my definition here, I mean distance to the nearest neighbor with respect to the Euclidean metric. So the question is, how many different distinct distances to nearest neighbors can there be? And I'll show you a picture here. This is in dimension 2. Wait for that thing to go away. And here I'm picking alpha to be whatever this number is here. And the picture here, if you look at the pink points, these are the multiples of alpha: 1 alpha, 2 alpha, 3 alpha, 4, 5, 6, 7. Of course, it wraps around the torus at the boundaries. And I'm taking 12 points. The blue edges here, they're directed edges, and each blue arrow points from the point in the orbit to its nearest neighbor. And so you can see that the nearest neighbor to the point alpha is going to be 12 alpha. You can see that the nearest neighbor to the point 6 alpha is going to be 5 alpha. The labels on the blue edges here they're labeling the different distinct distances that you see. And so in this example, we have a 2-dimensional example where Gn is equal to 5, okay? Because there's 5 distinct distances in the picture. Here's a 3-dimensional example. It's the same thing. I'm not going to explain all the details. This is the same thing, but just in the 3-dimensional torus. And if you look at this 3-dimensional example, if you just look at the biggest number on a label that you see, you can see that in this example, you have an example in 3 dimensions where G and the number of distinct distances is 7. Okay. So there are some people who studied this problem previously, but to our surprise, not a lot. We could only find a couple of references to this problem. The main one is this paper by Beringer and Schmidt. And what they proved, it's a really nice result. They proved that the number of distinct distances between nearest neighbors is bounded above by 3 to the d plus 1. And there's also a paper by Chevalier. And this one was a little bit hidden from us until he pointed it out. So he actually studied this problem as well, but he studied it with the Supernorm in place of the Euclidean norm. And what he proved in one of his papers is that in 2 dimensions, did I mention that is in 2 dimensions here? Oh, I actually forgot to say that in the slide. So this is for 2 dimensions. In 2 dimensions, the number of distinct gaps is bounded above by 5. That's for the Supernorm. And he also gave an example with 4 distinct gaps for the Supernorm. Okay. And all right, of course, what makes the problem difficult if you know anything about the 3-distance theorem, there's lots of different proofs. Like I said, there's probably over a dozen different proofs, but almost all of them somehow rely on being 1-dimensional. So they maybe use continued fractions or something like that, and they don't generalize well to higher dimensions. So the other thing that makes it difficult is, and you're going to see this feature in what I'm describing to you, the other thing that makes this difficult is that even when you have the right tools to study the problem in higher dimensions, you right away run headlong into these really simple to state, but extremely difficult, notoriously difficult discrete geometry problems, like estimating the Kissing number in RD. So what we're able to prove in our paper, there's a number of results, but one of the ones that I want to try to focus on is this result where we bound the number of distinct distances between points in a total rotation in a higher dimensional torus. So what we prove is that in 2 dimensions, the quantity Gn that I defined as bounded above by 5, and that's best possible. I just showed you an example with 5 gaps, so we know that that one is best possible. And what we prove in general for d bigger than or equal to 3 is that it's bounded above by the Kissing number plus 1. Okay, I probably don't need to tell you guys about the Kissing number. I think I probably know less about this than everybody else here, and definitely less than Oleg. If we have a question about it, we will ask him. So the Kissing number, though, if you don't know the definition, it's the maximum number of non-overlapping spheres of radius 1 in d dimensions, which can be arranged so that they all touch the unit sphere in exactly 1 point. And this is beautiful, beautiful stuff. Here's a bound. If you've never seen this before, I doubt that there's anybody who's never seen this before. Here's a table of known bounds for the Kissing number in dimensions up to 24. The ones in boldface are best possible. Of course, the dimension 4 bound was proved by Oleg in 2003. It was published in Annals in 2008, I think. And besides that, these are the only dimensions. 1, 2, 1. Okay, 2 is easy. 3 and 4 are not easy. 8 and 24 are not easy. But those are the only dimensions where those are known to be the best possible bounds. When you translate that into the language of the bounds here, it gives you the bounds 1325 out to 555. But we kind of doubt that any of these are best possible. We think that probably if you put a little bit of extra information into the problem, you're going to be able to get these bounds down. So I'll talk about that at the very end. I'll give you a conjecture of what I think it is in 3 dimensions. All right. one more thing about the Supernorm problem. If you change the definition, and we went ahead and looked at this as well. I looked at this with an undergraduate student who's working with me last semester, because after we found the paper of Chevalier, we realized that some people were interested in the Supernorm corresponding problem for the Supernorm instead of the Euclidean norm. And so what we were able to prove for the Supernorm problem is that the corresponding number of gaps is bounded above by 2 to the dimension plus 1. And we're also able to prove that that's best possible in dimension 2. And we're able to prove that it's best possible in dimension 3. So the proof of this, I would say, the proof of the upper bound is a lot easier than the corresponding result for the Euclidean norm. It's easier, I'll say that way. But to find the example where you get equality here, that's also not, it's a non-trivial part of the proof. I mean, it's easy to show you the example after you've got it, but it took a while to find the example. Okay, I want to make a comment here in case anybody had thought about this while I was introducing the definition. You know, I introduced this definition of number of distinct distances to nearest neighbors as a generalization of the Three Gap Theorem. But if you go back to the Three Gap Theorem, if we had defined the gaps here as distances to the nearest neighbors, then if you look at it, every vertex that's adjacent to a purple edge here is also adjacent to a blue edge. And so that means that for the number of distinct distances to nearest neighbors in this problem, we would have only had 2 instead of 3. So it's really not a direct generalization of the original Three Gaps problem. You can prove in the one-dimensional case here that even if you use number of distinct distances to the nearest neighbor, you still get 3 as the best possible bound. But in general, those two things are not the same. And so where am I here? In order to have a kind of a more robust generalization that allows for that the idea of looking in certain directions, we make this definition. We say, pick your favorite set of directions in d dimensions. So pick a subset of the unit sphere in RD, and then only look in that direction when you're looking for nearest neighbors. So for each point little n alpha in your orbit, you take the closest point m alpha modulo 1 with the property that the vector pointing from m alpha to n alpha is pointing from n alpha to m alpha, is pointing in the direction of your set of allowable directions d. Okay. So this is just a more general definition of the gaps in the higher dimensional problem. And then I'm going to call Gn of d alpha. I'm going to let that be the number of distinct distances to nearest neighbors in the direction of d. Now, what we can prove for this more general version of the problem is that, well, okay, we're considering here, I'm showing you in 2 dimensions. In 2 dimensions, let's suppose that we're going to confine ourselves to look in a cone. And let's suppose that the cone has angle tau. If the angle of the cone is bigger than pi, then we can prove that the number of distinct distances in the direction of that cone is bounded above by, and well, the right-hand side depends on what tau is. One feature, though, of the bounds that you should look at is that when tau approaches pi from the right, the bound tends to infinity. And so the point here is that also for the problem of looking at nearest neighbors in certain directions, we can use our machinery to get certain bounds. And the bound is finite as long as the cone angle is bigger than pi. We also have a complementary result. And the complementary result is that as soon as the cone angle is less than pi, I'll show you. So, well, I'll just tell you first, and then I'll show you. Our complementary result is that as soon as the cone angle is less than pi, then the typical behavior of this quantity Gn of d alpha is that it's unbounded. And I'll show you the statement of that result. This is actually stated for arbitrary dimensions. What our result says for arbitrary dimensions with small cone angles is, okay, I'll just go ahead and explain it the way it's explained here, is that if you pick a set of directions with non-empty interior, which is contained in an open hemisphere of the space, so that corresponds to picking a cone angle, or actually it doesn't even have to be a cone, to picking a region which is contained in a half plane in 2 dimensions, then for almost every choice of alpha, the set P here is a set of full Lebesgue measures. So for almost every choice of alpha, the number of gaps is actually unbounded. In fact, if you read all the details here, you can even sample the number of gaps along any sub-exponential sequence. So for example, along a polynomial sequence or something, and you'll have unbounded gaps along that sequence. So this shows you that there's a kind of a cutoff. If your cone angle is large enough, then at least in 2 dimensions, you're going to have finite. You're going to have bounded gaps. Otherwise, okay, I need to move on. Otherwise, when it gets too small, you're going to have unbounded gaps. Okay, I've got 10 minutes, and I think that's enough time to try to explain the main idea in the proof. The main idea in the proof is to, in the proofs of all of the results that I showed you for linear forms and for the higher dimensional torus problems, is to reformulate the problem about the number of gaps as a problem about functions on spaces of unimodular lattices. And so this is a pretty full slide, but if you could understand the definition of FD, then you'll be able to understand what I'm trying to communicate here. This matrix M, or this element of this quotient space M, think about it as a d+1 by d+1 matrix with real coefficients. If you have a d+1 by d+1 matrix with real coefficients, the rows of that matrix span a lattice in Rd+1. But of course, the lattice is only unique up to left multiplication by an element of SLD+1z. And so that's the reason why I'm calling this a space of lattices. Unimodular means that they have determinant 1, so that the volume of the fundamental domain is 1. So think about elements M either as lattices or as d+1 by d+1 matrices, and pick your favorite lattice M and pick a number t from 0 to 1, and then define a subset of the lattice points in the lattice M by taking the UVs with the property that the first component U lies between -t and 1 - t, and the rest of the vector V here points in the direction of D. So the set Q sub D of MT, remember D is your set of directions, and T is just some parameter that you're varying. It carves out a slice of the space, and then it takes all the lattice points in that slice. And then the function FD, what it does is it looks at all the lattice points in that set, QD MT, and it takes the smallest possible value of the length of the last D components, okay? The reason why this function F sub D is important in this problem is because you just by some basic arguments, you can show that the nearest neighbor, the distance to the nearest neighbor of little n alpha in the direction of D is a scaled value of the function FD at a particular lattice and for a particular choice of the parameter. The particular lattice, of course, it has to depend on alpha and capital N, otherwise you wouldn't believe me what I'm telling you. So it's the lattice generated by the rows of this matrix, the product of these two matrices. And if you believe me about that, then the important quantity that you want to try to study is you want to try to study the number of distinct values taken by this function F sub D of MT as the parameter T varies from 0 to 1. So that's what I'm calling G sub D of M. Now, I think this line on the slide is not 100% true, but it's philosophically true, and it's 99% true that the number of gaps in the gaps problem that we defined before is equal to the value of this function script G sub D at the lattice A sub n of alpha. The reason why this is a useful connection in the problem, I would say it's sort of for 2 reasons. Reason number 1 is by adding this extra dimension in the problem, you move from thinking about orbits of points in the torus to thinking about lattices, which are in Rd+1, which are groups. And so they have this extra additive structure that you can use. And number 2, if you know a little bit about homogeneous dynamics on spaces of unimodular lattices, then you might recognize that the role of the parameter capital N here is right multiplication by a sequence of matrices that's following the geodesic flow on the Riemannian manifold, SLD+1R mod SLD+1Z. So that's an ergodic action on the space. And you can use that together with some other arguments from homogeneous dynamics to try to understand what happens for typical values of alpha. So when you're trying to prove that something happens for a typical value of alpha, for almost every alpha, what you need to do is you need to come up with examples of lattices in the space that exhibit the behavior that you're interested in, or maybe neighborhoods of lattices that exhibit the behavior that you're interested in. And then you know that as you vary n, you're going to visit those neighborhoods infinitely often. So that's really the power behind this machinery. And I'm not going to stay too much about I'm not going to go in the direction of ergodic theory because I only have 5 or 6 minutes left here. I'm going to tell you really quickly how the discrete geometry thing comes into the problem. And I think I only have like 3 slides left, so this is going to be pretty quick. So the idea is this. Let me just now try to explain how you get the 5 gaps and how you get the kissing number plus 1 out of this. And I'm going to skip a lot of details, but I'm going to tell you the important ones. So the important thing is this. You write out all the different lattice vectors that correspond to the different values that your function f sub d takes. So in this example, if it takes k values, it means the number of gaps is going to be k. And then you just argue that if you had too many vectors like this, you could find some linear combination of them. So you're using the lattice structure, which together with the definition of FD would give you a contradiction. And so the lattice structure together with the definition of this function FD impose certain geometric constraints on the problem. And then those geometric constraints are what give you the bounds that I was explaining before. And I'll give you a couple of examples. So the first example is this. It's pretty easy to prove. We use this bound. This bound gets you a long way. It's pretty easy to prove that if the number of gaps function, or this function script g of a lattice is equal to capital K, here I'm considering nearest neighbors in any direction, then for all vectors vi and vj with I and j less than k, the length of the difference between the two has to be bigger than the max of the two lengths. Okay, so this just comes from the lattice structure and the definition of the function f. And what it tells you, if you just translate it into the corresponding geometric statement, it tells you that if you have two vectors vi and vj with I and j less than k, then the angle between them has to be bigger than pi over 3. Well, I mean, we're working in d dimensions, and so that almost immediately gives you the bound that the number of gaps is bounded above by the kissing number plus 1. So this is a really short way of explaining how you can get this result out, how you can get this part of the result out. Okay, now of course, in dimension 2, the kissing number is 6, and so this would give you the bound of 7. But I told you that we can actually show that 5 is the bound in dimension 2. And so how do you get from 7 down to 5? Well, to get from 7 down to 5, you need to go back to the definition of the function f, and you need to play around with the lattice. You need to play around with the vectors ui, vi a little bit more, and you need to extract another geometric constraint. And when you do that, well, you can prove that, and I'm pretty sure, yeah, this is in any dimension still. You can prove that in any dimension, if you have 3 vectors vi, vj, and vk with I less than j less than k less than capital K, when you form the linear combination vi minus vj minus vk, the vector that you get has to have lengths bigger than or equal to the length of vk. So when you specialize this observation to 2 dimensions, and there's a little bit of geometry that you have to work through here, but it's nothing that complicated. When you specialize this observation to 2 dimensions, what it tells you is that anytime you have 3 vectors, vi, vj, and vk with I less than j less than k less than capital K, the vector vi, it can't lie in the positive cone determined by the other 2. And if you just take that and you run with it, if you combine that with the first observation was that any 2 of these vectors have to push each other apart by an angle bigger than pi over 3. So when you combine that with the second observation here, what you can do is you can say, well, if you had 6 vectors, then the first vector v1 would lie in the positive cone of the vector to its right and the vector to its left, and that would give you a contradiction. And so that tells you right away that in 2 dimensions, the number of gaps is bounded by 5. If you want to see a real concise way of how you get these geometric constraints out and then translate them into the corresponding geometry problems, you can look at the Supernorm paper that I mentioned, that I wrote with this undergraduate, because there the geometry is a lot easier, but the underlying principle is basically the same. Okay, so to finish my talk, I just want to finish by asking this question. You know, what about the best possible bound for Gn when d is equal to 3? So the bound that we have is 13, but after extensive numerical analysis of this problem, we think that probably the best possible bound is actually 9. The 13 is just coming from the kissing number problem. We're not even using the second geometric constraint that I just now showed you, because we can't figure out how to get it to help you at all. I mean, maybe you can get it down to 12 or 11, but actually we think that probably in 3 dimensions the answer is probably actually 9. Okay, I'm going to go ahead and stop there. So thank you guys very much for your attention. If you're interested in any of the proofs, you can take a look at some of our papers on the archive.
Okay, thank you very much. Very interesting talk. Questions? We have 10 minutes actually before the next.
Hi, I have a question. May I ask? You hear me?
Yeah.
Yes, I have a question. So you have been focusing all the time on the upper bounds. And from what you are saying, it seems that to achieve the upper bound is a very non-typical behavior, since you said like to get some of the results, some of the examples, you actually needed to work quite a bit. Do you know anything about it? Can you say something about the typical behavior?
Yeah, let me say something because that is a really interesting. I also thought about this thing that you're thinking about, and it's a really good question. But actually, there's another theorem in our paper that I didn't put on here, which is that the typical behavior, because of the ergodic theory going on in the background, is that if you pick a point at random, and like let's talk about 2 dimensions. You know, we said the best possible bound is 5 as an upper bound, but the typical behavior is that you're gonna achieve 5 infinitely often. Because there are neighborhoods of lattices where you actually get 5 gaps. They're hard to find, but they are there. And so when you just let n vary, if you pick a typical point alpha, you're going to visit those neighborhoods infinitely often. So the typical behavior is that you achieve the best possible upper bound infinitely often.
Okay, so
numerically, they're very difficult to find.
That's
you
interesting.
know, it's kind of a weird thing, but but that is the typical behavior.
Thank you.
More questions?
Yeah, I have a quick question. So I was pretty interested in the connection with the Littlewood conjecture. Yeah, and I was wondering if there are some analogs here of the negative results in the style of Badzahin, Mashevitин, Villani. So
you mean like the bad IJ?
Right, something like that. Yeah.
The Schmidt conjecture thing. Yeah, that's related. That's really closely related. So what should I say about that? I mean, if you're in bad IJ, if you, I'm not going to have time to define what bad IJ is.
Sure.
If you're in bad IJ, what it means is that you can pick a certain 1 parameter subflow of the geodesic flow on the space where your orbit remains bounded. And that has certain implications for the gaps problem immediately. And the 2 problems are very closely related.
Okay. Oh, where could I read more on the relation between the 2? So which paper would be
so you can read it in my paper with Jens Markov, the top one here. That's where we prove this equivalence to the Littlewood conjecture.
Okay, thank you.
Yeah, so the two problems are connected because of transference principles in Diophantine approximation. You can read about it in the paper there. We give all the details.
Okay.
More questions? Actually, I have tons of questions, but I ask only one. What happened if you consider, you consider a square torus, right? But what happened if you consider some other parallelogram in 2 dimensions?
So in our paper, we consider because we're working in the space of lattices, we can consider any tori.
Yeah, sure.
So we get the result for all tori. So you don't have to mod out by ZD. You can mod out by something else.
But with the same Euclidean distance, it will be the same result.
So it's I think it's equivalent to saying we prove it for all flat metrics.
No, I should, because I remember you have some constraints for you said constraints for lattices. I mean, it's not in 2 dimensions. It works for some high dimensions there are, but okay. Say, let us consider just simple question. Let's consider a rectangle with sides 1 and square root of 2. It will be the same result?
Yes.
Wow.
Yeah. So that comes almost for free by virtue of the fact that we're working in this lattice framework.
Okay. Okay. More questions? It's always the most interesting case. You still look. You still will have the kissing numbers. It's also asymptotic exponential, right? So you improve, of course, asymptotically improve it, but it's not still exponential. And what do you think? It is a polynomial or just no way to get some?
Oh, the number.
polynomial
You mean the
about-
number of gaps? Number of gaps?
Yeah, I mean, I suppose
I don't know. I'm not sure. I thought about that before, but I can't remember where I left off thinking about that. So I'm actually not sure about the answer.
okay.
But the number of gaps is going to grow very slowly as a function of capital N, typically. It doesn't go to infinity, you know, it goes
Yeah,
out.
it's infinity, but it may be linear or some polynomial. But kissing number gives you also that exponential bound. Okay. More questions? Okay, thank you very much.